All right, thank you. This talk is about curve fitting with least squared relative errors. Now, suppose you're measuring currents. You start doing several measurements. Let's say you're reading 100 milliamps. And your readings tell you that you have an error of plus or minus 5 milliamps. Okay, but then you're reading 1 amp. And your equipment also gives you the same error. Well, if you do a curve fitting with information like that, the ordinary regression will treat each error with equal importance. But that might not be the case for you. You might be more concerned about the error with smaller value because the percentage error or the relative error is higher. And this is what this talk is about. Of course, there was an interesting world reaction for the new algorithm. Carl Gauss, the guy who was behind ordinary regression, was not really happy, but hey, you can't all keep him happy. In ordinary linear regression, we take the simplest model, linear regression. You have y equals the intercept a plus the slope b times x. And when we minimize the sum of squared errors, we have the individual error equals the left-hand side minus the entire right-hand side. The difference for each observation gives us the error for that observation. Now, in the case of minimizing the sum of squared relative errors, we have pretty much, for the individual values of the relative errors, the left-hand side minus the right-hand side, all divided by the left-hand side, which is equal to 1 minus the intercept a over y of I minus b times x of I over y of I. To calculate the slope and intercept for the relative error, we minimize L, which is the sum of the squared relative errors indicated by that beautiful expression. Actually, it's very messy because it doesn't follow the kind of summations we have been seeing for the last 30 years. To calculate the slope, it's the ratio of two expressions with summations. And as you take a few moments to look at the summation, none of them looks like something our calculators are pre-programmed to accumulate because we're doing relative errors. The intercept is a little bit better, but not by much. So when we look at these, and if some of you remember the equations for the regular ordinary regression, you can see that there's quite some difference between relative error and the ordinary regression counterpart equations. And this is just for the basic linear regression. It gets even better if you do quadratic fits, cubic fits, and, heavens forbid, multiple linear regression. For example, for multiple regression, we have the matrix version, and some of you know the equation. This is in matrix and vector form. And with the graphing calculators, you can execute that very easily. X here is the matrix of the independent variables. Usually has a column of ones, either the first one or the last one, to account for the intercept. And then all the other columns represent the independent variables and or their transformations, if you're doing quadratic or whatever polynomial fits. Y is the vector of the dependent variable, and then B is the vector of the regression coefficients that we like. Now, in the case of the matrix version for the relative error, the reference you will see at the end, I got this from, we introduce a new matrix called D. And D is a square matrix which matches the size of the number of observations with zeros all over the place except for the diagonal elements, where each diagonal element is equal to 1 over y of I. So already in matrix form, it gets a little bit messier. Well, right there I said, I'm no statistician, And I cannot go on trying to figure out what the correlation coefficient and standard errors, all that is messy. So trying to take the lazy way out, I said, is there a way we can transform relative curve fitting into equivalent ordinary curve fitting? Now, if this was a Star Trek convention, Captain Kirk would say, there must be a way. Of course, well, some pessimist hopes that we choke on it, so. But Mr. Optimist, moi, says, yes, Captain, there is a way. Well, let's take a look at the sum of the squared error expression. L equals 1 minus that ugly expression there. Now, if we look at it in terms of ordinary regression, it's like we're saying 1 equals a over y plus b times x over y. Okay? Well, this is a weird, ugly, and heretic model. We'll look at it again. Now, this model is a multiple regression model with no intercept. And then all the values of, there's a new pseudo dependent variable, I'm going to call it O. Every value for O is 1. And here, X and Y, we're going to regard them as independent variables. So we're kind of turning the tables around. If you did the testing like I did and used Excel, there's a data analysis pack and there's a regression tool. And when you do the regression, you have to check in the constant is 0 checkbox. If you don't, you will get a constant equal 1 because all your dependent variable values are 1. And your slopes will all be zeros. But if you tell it that the constant is 0, then you will get the values for the slope and intercept of the relative regression. Now, if you're doing direct calculation using the matrices, make sure that matrix X has no columns of 1s because you don't want the intercept. Instead, these ones will migrate over to the new pseudo dependent variable O. That will be, all the 1s will be there. So let's look at what we've done so far. For example, we have an ordinary linear model, y equal a plus b times x. That becomes O equals 1, and then we're taking the right-hand side, dividing it by the left-hand side. So that's the linear model for relative error. If we have a quadratic model, again, we end up with O equal value of 1 for every element, and then we've taken the right-hand side divided by the left-hand side, and treating y again as an independent variable. And same thing goes with a simple case of multiple regression, when we have originally variables x and z as the independent variables. By dividing them all by y, we end up with the expression at the bottom. And you kind of get the drift. Every time we're dividing by 1, creating a new pseudo dependent variable O, and then y becomes temporarily, we treat it like an independent variable. I'm going to present 3 cases where I simulated errors. The way I did, I took each model, I had a theoretical model. I gave it a slope, intercept, whatever it needed. I calculated theoretical values of y. And then I created a function that calculates a Gaussian normal error around that y. The mean value is 0, but the standard deviation, I used a percentage, 5, 10, and 20% of the theoretical value of y. So I have the theoretical value of y, a random normal error, I add them both, and I get a simulated observed y. And that's the one I use for the regression. This approach is very good because then I don't have to worry about what my model is, because I'm generating the error based on the value of y, not what the model is. I don't care how many variables I have, independent variables, what the model is, it doesn't matter. The first case of simple linear regression, I noticed that the relative error yields high correlation coefficients, higher than ordinary regression. And that's sort of like we're really cheating, because it's really a multiple regression where the intercept is forced to be 0. So you expect that the correlation coefficient to be higher. What is interesting, and because we're tired and it's late, these conclusions pretty much apply for the other types, that when we increase the error over small ranges of x values, the ordinary regression suffers from a lower values of correlation values than the relative error. So the relative error pretty much maintains its own. Here's a case of, originally the straight line was 5 plus 2x. And of course I added the normal errors. I have three groups of three ranges. The first range is from 1 to 2.14. So the values stay pretty much in the same order of magnitude. And then in the middle I have from 1 to 12.4. So I'm expanding my range by an order of magnitude. And then the last three, I'm going from 1 to 115. So I'm going two orders of magnitude. And then in each set, I'm going from standard error from 5% to 10% to 20%. So notice here, so the pointer works, the R square, it goes from 0.99 and how it just does a free fall, like a lead balloon it shoots. Now, in the second range, when the range is wider, it goes just to 0.76. And then in the wider range, the degradation is not terrible. Now, the relative error regression also suffers degradation, but the values are not that terrible. And like I said a minute ago, because we're tired, that's pretty much the trend for all the various models. This is a snapshot, because I ran the simulation many times. This is a snapshot of the curve. And I've noticed throughout, of course, the zigzagging line, these are the simulated observed values of y. The green line is the linear regression, and the magenta line is the relative error. And the relative errors seem to always go kind of lower because it's trying to negotiate with the relative errors, while the linear regression is trying to compromise with all the errors, treating them all equally.
In Namir?
Yes.
If you go back to that previous slide for a second, what adjustment do you make when the predicted value would be 0? Because if you go back,
you hit it on
constant.
You can't have 0. Yeah, that's
divide by 0, right?
Yeah, you cannot. That's the only Achilles heel for the method. You are right. In the case of a quadratic curve, we have pretty much the same conclusion, that the relative error gives us higher correlation coefficient than ordinary regression. And again, for narrower ranges, the curve fit, the correlation coefficient drops more significantly than that of the relative error. One of the things I found out, because I tried here a couple of cases where the quadratic curve has a minima, maxima, or just sort of going on. And I discovered that the presence of minima and maxima causes the ordinary regression fit to deteriorate even more, to suffer more. But when there was neither maxima or minima in the regression data, the deterioration was not as bad. And again, I have the same three ranges. This is the first table is for the ordinary regression, and you can see very low values here. Values are not that bad here, and kind of maintain here. While for the relative error, again, they do suffer, but it's not a terrible defeat. And again, here's a sample plot for the quadratic fit. And the the blue line of the zigzagging is the simulated observed data. The brown curve is the linear regression, and relative regression is the green one. Again, it's trying to hug the lower values because it's concerned about relative regression and trying to be close to the smaller values. Multiple regression, again, pretty much the same thing. And this is, I updated the thing. We have the same results again, narrower ranges that experience a higher percentage of standard error will suffer more, while the relative error will maintain a better correlation. Conclusion, the relative error regression is closer to the small value of observation. That's why usually its curves are below the ordinary regression curves. Now, if you give both type of curve fits data with no error, you'll get exactly the same results. The degradation of ordinary regression increases for smaller ranges with big percentage error, as I showed. And of course, I've conducted the relative error regression assuming that the relative error are normally distributed, which is also a basic assumption in ordinary regression. I did not want to violate that, because if there's a statistician here, he would have probably shot me on sight. Anyway, conclusion, of course. This is supposed to be stupid is as stupid does. I have nobody to defend me, but Uncle Siggy here, he doesn't like Gauss. It's funny. Actually, tomorrow will be the 73rd anniversary of his death in England. He was euthanized. But I'm glad he put on a good word at the conference. This is my reference. After I did most of the work, I found this reference, and this British mathematician or statistician had the same thinking as I did. I was just amazed how our approach was similar.
So,
anyway.
What it's doing, it seems to me, is trying to keep ordinary linear regression from chasing after the outliers. Really, right?
Yes.
Because ordinary linear regression is really affected by some value that's way off.
Ordinary regression is trying to compromise every error with equal weight.
And since there's some of the squared errors, the outliers really veer it off. Whereas this, using the
relative or percentage, he calls it percentage.
It's not as greatly affected by them.
Yes. Like with my opening example, you might be worried more about the error for the 100 milliamps, that 5 milliamps error, than the 5 milliamps error in 1 amp. You know, and especially when you're doing curve fitting and you're trying to predict in area of low values, if you are more concerned about percentage error, relative error is better. The reference quotes some researchers that did Monte Carlo simulation and found that relative error gave coefficients closer to the theoretical coefficients, better values than ordinary regression. So, anyway, thank you, and.
Well, we're supposed to close.